Hey everyone, welcome to the new Demystifying Technology series, where we're going to be looking under the hood and understanding how things work. And in this first episode, I'm going to show you what happens when we click this button here in the Yubikey. The Yubikey is a multi-protocol security key, which I use as a second factor to protect my accounts. I have a couple of accounts protected with Yubikeys, and one of them is AWS. So it's as easy as inputting my username and password, and then after that, I just need to click the button in my Yubikey, and I'm good to go. It's a very cool technology, but it's even cooler when you understand what's happening inside this key here. So let's take a look how your Yubikey generates one-time passwords.
In order for me to see what information the Yubikey is sending to my computer, I'm going to write a very simple C program that's going to read from the Yubikey and present the information in the terminal. So here at the top I have my headers, so the standard input-output library and the standard library. Now here in my main function, I need to declare a string. So I'm going to call it Yubikey underscore code. Now I need to allocate space for this variable. When you touch the button in your Yubikey, the Yubikey sends a 44 character long string. So in that case, I'm gonna allocate 45 bytes because I need 1 byte for the null terminator. Now I'm just gonna print a message. So print f, touch your Yubikey, and then I'm gonna read it. %s Yubikey underscore code. At the end, let's just return 0. Alright, let's compile this and see what happens. Now let's run it. Okay, so this is the information that my Yubikey sent to my computer. And you might think that this is the OTP that is generated, but it's actually not the OTP. I mean, the OTP is here, but there's one more information in the string together with the OTP. So let's go back to the code and split the string. So first thing I'm gonna do is to declare a couple of variables. So I need a variable which is called Yubikey underscore ID, and I'm going to allocate 13 bytes. Then I need another variable with 33 bytes, and that's going to be the OTP. And I also need some integers, so I and j. Now after I read the Yubikey code, I need to declare a for loop. And here I'm just gonna put whatever I read from the code, Yubikey code, into Yubikey ID. And when we're done, I just need to assign the null terminator. Now I'm gonna do the same thing for the OTP, but here it needs to be a little bit different because the I is gonna start at 12. But because my string needs to start at 0, I need another counter. So j will start at 0. And both of them are gonna be incremented. So my OTP variable and the position j is gonna receive the Yubikey code and position I. And then same thing at the end, just need to provide a null terminator. And here I forgot to provide the index. So the index is gonna be I. All right, now we need 2 more print statements. So this is for the Yubikey code. And I need one for the Yubikey ID. And another one for the OTP. Okay, now let me run this twice more. One thing you can notice here is that my Yubikey ID never changes. This is just basically an identifier for my device. Now the Yubikey OTP, that one changes all the time. And this is the dynamic OTP that is generated. One thing you notice though, is that for the public ID and the OTP, they have characters which seem pretty much random. I mean, you might think this is an hexadecimal, but it's not because you've got letters like V, R, L, etc. So now let's understand what format the Yubikey is using here. When you hit a key in your keyboard scans code to your computer. It doesn't send the actual character. For example, if you press the letter A, your keyboard doesn't actually send the letter A. It sends a scan code to your computer, and your computer is going to take that and translate it into the letter A. Now, when we compare two different keyboards, like the American keyboard and the German keyboard, you see that in the American keyboard you have Y here at the top, but in the German keyboard you have Z. And so if you configure your computer to read from a German keyboard, but you actually have an American keyboard, if you press the letter Y, your computer is going to translate that into Z. So you see that there is some ambiguity here, because pressing a key in the same position in two different keyboards might result in two different letters. And the same thing would happen with the French keyboard, where you'd have A instead of Q and Z instead of W. With that in mind, to reduce these ambiguities, Yubikey decided to create the Modified Hexadecimal Encoding, or ModHex. And to translate from Modified Hexadecimal Encoding to hexadecimal, you simply need to take the characters that are generated by your Yubikey and search for them in the 2nd, 4th, 6th, and 8th columns. When you find the letter, the hexadecimal equivalent is going to be right on the left. Let's see an example. Let's say that we have the following string in ModHex format, ENUR. Starting with E, we can find E right here at the bottom. And so that means that the hexadecimal equivalent is going to be 3. For N, the equivalent is going to be B. For U, it's going to be E. And for R, it's going to be C. And at the end, the equivalent of ENUR in hexadecimal is 3BEC. And from there, you can easily translate that into binary. Now, the next thing we're going to do is to implement a function in C that takes a ModHex string and returns an hexadecimal string. And before we code, I just wanted to go over the logic with you first. I'm going to assign indexes to our columns, and because it's C, it doesn't start at 1, it starts at 0. So instead of having from 1 to 8, we actually have from 0 to 7. And the logic is going to be, for every ModHex character, we're going to look for them in the columns where the column index plus 2 needs to be a multiple of 2. For example, if we're looking for the letter V, we'll find V in the column of index 7. Now 7 plus 1 is 8, which is a multiple of 2. When we find the ModHex character in the matrix, we're going to retrieve the letter immediately before in the same row. So if we're looking for V, we're actually going to retrieve F. But now let's say that we're actually looking for F as the ModHex character. If our function finds F in the column 6, 6 plus 1 is 7, which is not a multiple of 2. And in that case, it would ignore that character. If we're looking for F, it should actually find F in the column 3, in which case 4 would be retrieved. Now that you understand a little bit how it would work, let's go back to our code and implement this function. Let's now create a function that is going to take a string in modified hexadecimal encoding format and convert that to hexadecimal. So I'm just going to declare a function here at the top, which is going to return a pointer to a character, which is a string pretty much. So modx to x, and it's going to get a string and an integer, which is the size of the string. Now let me copy this, go here at the bottom, and need to declare some variables. So let's say s and length. I need to declare a variable for my hexadecimal string. So this is going to be a pointer to a character, and I'm just going to allocate some space. Len times the size of a character. And I also need some counters, some integers, so I, j, and k. And I need that matrix that we saw in the slides, which is right here. First thing I need to do is to read character by character of the string that we're getting the function. So k is going to start at 0, Okay, it's gonna go until the length of the string. Now for every character of that string, we're gonna have to find it in the matrix. So we're gonna have to traverse the matrix as well. For I starting at 0, and I is gonna be the column, the row actually. And you see that 1, 2, 3, we have 4 rows. So I actually here should be 0, and I less than 4. So this is for the rows. Now we need a for loop for the columns. So J gets 0, J, and we have 8 columns. J++. Now remember what I said. We need to look for the modified hexadecimal characters in the 2nd, 4th, 6th, and 8th columns. In that case, I need a if statement. And first, I need to compare the character in the string to the character in the matrix. I for the row and J for the column. This is the first condition. We need to find the letter. The second condition is to make sure that we're looking at the right column. And because C, the index starts at 0, not at 1, I can't compare to 2, 4, 6, or 8. What I'm gonna do then is to see if the column index, which is in this case is J, is multiple of 2. So what I'm gonna do here is J plus 1 mod 2. That needs to result in 0. So if J is 1, 1 plus 1, 2, 2 mod 2, that results in 0. Same thing for 3, 3 plus 1, 4, mod 2, 0, 5, and 7, which is the last column. Okay, so now let's do xk, and that's gonna get the matrix. This is the row, but now the column is J minus 1 because we want the one immediately before. So again, if we're looking for V, we actually want F for the hexadecimal. If we're looking for R, we want C, and so on. All right, that looks good. Let's go here and make sure we assign the no terminator to our string. And let's return X. All right, back to our main function. I'm gonna declare a string called X as well. And I'm gonna call the function ModHex to X. And the argument's gonna be the OTP, because that's what I want to convert. And the length, I'm gonna say 33. So now let's print that whatever we get back. So hexadecimal, and here it's gonna be X. Okay, this looks more familiar to us. As you can see, the hexadecimal string is the same length as the OTP in ModHex format. So my Yubikey ID has 12 characters and the OTP will have 32 characters. Now just to finish things off, let's convert this to binary. So at the top, I'm gonna declare the return is gonna be a pointer to char, and this is gonna be X to binary. So first thing I'm gonna do is declare a static char because we need to be able to return this variable to the main function. Then the length is gonna be 129 because we're gonna have 128 zeros and ones plus the null terminator. Then after that, I just need a counter to start at 0. And this is just a very simple way to convert to binary. We're just gonna read every character of our hexadecimal string and just look for it in the switch case statement. Whenever we find it, we just copy the equivalent in binary to our bin variable. And then at the end, just need to make sure that we have our null terminator. And here it's gonna be actually I times 4 because the I is following the hexadecimal string, but the bin string is actually 4 times bigger because for every hexadecimal, we actually have 4 characters for the bin variable. So that's why I'm doing I times 4. And that's gonna get my null terminator. Then at the end, I just return bin. All right, so here, let me just fix this quickly. So this is gonna be the Yubikey OTP in hexadecimal. And now we're gonna have the OTP in binary. All right, let's run this one more time. And that's right, I just forgot to include the string header because we're using strcat. So let's include this. All right, that worked. Now let's run it. Okay, we have our binary, and if we copy this, you see here at the bottom that it has 128 characters. Of course that this has 128 bytes for my C program because it's just a string, but when the hexadecimal is converted to binary for the computer, it's gonna have 128 bits. Now you might be wondering what kind of information we have in these 128 bits. Let's take a look at that next. As you now know, the one-time password generated by your Yubikey when converted to binary has 128 bits. The first 48 bits are dedicated to this private ID. And according to Yubikey, the private ID can be used to store a private identity, or otherwise it can be all set to 0. And there might be cases where a random number is going to be assigned to the private ID. Then the next 16 bits are used for the usage counter. And the way this works is whenever you plug your Yubikey and you power it up, the usage counter is going to be incremented by 1. And even though it's 16 bits, your Yubikey actually just uses 15 bits. And the reason for that is because in Yubikey 1, the 15th bit was actually used to indicate when an external keyboard was used instead of the integrated button. And if the usage counter ever reaches the maximum number, which means 15 ones, the usage counter would stop there. But it would actually take a long time for that to happen. Just so you have an idea, if you used your Yubikey 5 times a day for an entire year, it would take you around 18 years to max out the usage counter. And that's if you plug and unplug 5 times a day. And if you plan to use your Yubikey for 18 years, I mean, just think about technology how it was before 18 years ago. It's probably going to be the case that in 18 years' time, something will have replaced the Yubikey. So I think it's safe to assume that we're not going to max out the usage counter. Unless something goes wrong, in which case you can actually reset your key and reset the usage counter. Now you might be wondering, what this is used for? Basically, when you use your key for the first time and you hit the button, let's say that the usage counter is going to be 1. If you try to verify the Yubikey one-time password with a verification server, the verification server is going to have 0 as usage counter. And because the usage counter in your OTP is 1 and the server is 0, your OTP would be accepted. And then the server would register that your usage counter now is 1. Next time when you plug your key again, let's say the usage counter is going to be increased to 2. When you send your OTP to the server is going to see that the OTP usage counter is 2, and your OTP would be accepted. So basically, whenever you send an OTP to a verification server, the usage counter needs to be higher than the server. And the reason that they decided to do that is to avoid replay attacks. Let's say that you're trying to log into your account, but for some reason your OTP is being exposed. When you log in, if your usage counter is 2, that means that the usage counter in the server is also going to be 2. If the attacker gets a hold of your key and tries to log into your account, the OTP that the attacker is using has a usage counter of 2, but the server also has 2. That means that the server is going to consider this as a replay attack because the usage counter is not higher than the server. I hope you get the idea. Then we have 24 bits for a timestamp. And the way this works is that whenever you plug your key and you power it up, this field is going to be incremented at a rate of 8 Hz. And to translate this into English, the timer would rep around every 24 days. And this field might also be useful for the verifying party because they know the time elapsed between 2 subsequent OTPs received during the session. Then next we have the session usage counter, which is 8 bits long. And as far as I understood from the Yubikey documentation, the difference between the usage counter and the session usage counter is that the usage counter is incremented every time you plug your Yubikey to your computer, but the session usage counter is incremented every time you touch the button.
And also, if you max out these 8 bits, the session usage counter is going to be reset and the usage counter is going to be incremented by 1. The next 16 bits are dedicated to a random number, which is generated by an internal random number generator which is in your key. So there's not much to explain here, it's just a random number to make your OTP truly unique every time you touch the button. And finally, the last 16 bits are dedicated to the checksum, which is just to verify the integrity of the data. When the OTP is generated, the algorithm calculates the checksum of all of the bits, excluding the checksum itself. But when the OTP is being verified, the server calculates the checksum of all of the bits, including the checksum itself. And that should result in a fixed residual of F0B8 in hexadecimal. And if that's the case, the checksum is valid. So there you have it. Now you understand all of the components of the Yubikey OTP. But just to give you a very big summary, when you plug your Yubikey into your computer recognizes the key as a USB keyboard. Then when you touch the button, here's what happens. The algorithm in your key is going to take the private ID, the usage counter, the timestamp, the session usage counter, and the random number and calculate the checksum. After the checksum is calculated, it's going to be appended at the end. The algorithm would then take this 128 bits long string and encrypt using an AES 128 key. And when the encryption is done, the data is going to be converted into this modified hexadecimal encoding format. Once the computer gets this information from your key, it's going to send to the verification server. The verification server will then take this ModHex string, convert it to binary probably, and it's going to decrypt using the same symmetric AES 128 key. Once the data has been decrypted, the validation server is going to make sure that all of the fields are valid, including the checksum, the private ID, etc. And then the last step before confirming that your OTP is valid is to make sure that the usage counter that came from the key is actually higher than the usage counter that the server has. And if that's the case, your OTP is going to be valid. I hope that gave you an idea of how a Yubikey works, and I'll see you in the next Demystifying Technology video.